This is SpaceTime Series 21, Episode 43. Coming up on SpaceTime, antimatter lightning beamed from the eyewall of a hurricane, the first new Shepard test flight for 2018, and China's new mission exploring the far side of the moon. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A beam of antimatter generated by a terrestrial gamma-ray flash has been detected for the first time, shooting downwards out of the eyewall of a hurricane. The discovery, reported in the Journal of Geophysical Research, was made by a storm-hunting aircraft as it flew through the eyewall of Hurricane Patricia, which battered the west coast of Mexico in 2015. Hurricane Patricia was the most intense tropical cyclone ever recorded in the Western Hemisphere. The antimatter burst was observed by an instrument aboard a specially equipped hurricane-chasing WP-3D Orion aircraft operated by NOAA, the National Oceanic and Atmospheric Administration, America's Weather Bureau. The Orion flew through the eyewall of the storm at its peak intensity. Amid the extreme violence of the storm, scientists observed something new: a downward beam of positrons, the antimatter counterpart of electrons, creating a burst of powerful gamma rays and X-rays. The positron beam was the downward component of an upward terrestrial gamma-ray flash that sent a short blast of radiation into outer space above the storm. Terrestrial gamma-ray flashes were first detected back in 1994 by space-based gamma-ray detectors. They occur in conjunction with lightning and have now been observed thousands of times by orbiting satellites. The instrument which detected the antimatter beam is called a DEL, which stands for Airborne Detector of Energetic Lightning Emissions. It's designed to observe terrestrial gamma-ray flashes, or TGFs, up close by measuring X-rays and gamma-rays from aircraft flown into or above thunderstorms. The scientists who built the instrument say they weren't surprised to detect the positron beam, even though it was the first time anyone's actually observed the phenomenon. One of the study's authors, Professor David Smith from the University of California, Santa Cruz, says the discovery is the first confirmation of that theoretical prediction, and it shows that terrestrial gamma-ray flashes are piercing the Earth's atmosphere from the top to the bottom with high-energy radiation. Now, this event could have been detected from space like almost all other reported terrestrial gamma-ray flashes as an upward beam caused by an avalanche of electrons. But Smith and colleagues saw it from below because of a beam of antimatter positrons which were sent in the opposite direction. So what all this means is that terrestrial gamma-ray flashes can now be detected using ground-based instruments by their reverse positron beams without needing to fly an aircraft into the eye of a hurricane. Smith and colleagues detected the beam at an altitude of 2,500 metres, meaning the detector could have sent it down to around 1,500 metres, and that's about the altitude of Denver, Colorado. So what all this means is there'd be a lot of places around the planet where you could in theory see these things using an instrument placed there on the ground during a thunderstorm. Despite confirmation of the predicted reverse positron beam, there are still many unresolved questions about the very mechanisms driving terrestrial gamma-ray flashes. So, what do we think's going on? Well, strong electric fields in thunderstorms can accelerate electrons to near the speed of light. And these relativistic electrons are emitting gamma rays when they scatter off atoms in the atmosphere. The electrons can also knock other electrons off atoms and accelerate them to high energies, creating an avalanche of relativistic electrons. But a terrestrial gamma-ray flash, which is an extremely bright flash of gamma rays, would require a really large number of avalanches of relativistic electrons. And the thing is, scientists still don't understand how it could get so bright. The source of the positrons is straightforward enough. It's a pair production, in which a gamma ray interacts with the nucleus of an atom, creating an electron and positron particle pair. And since they have opposite charges, they're accelerated in opposite directions by the electric field of the thunderstorm. The downward-moving positrons produce X-rays and gamma rays in their direction of travel when they collide with atomic nuclei in the atmosphere, just like the upward-moving electrons do. So what the authors saw from the aircraft were gamma rays being produced by the downwards positron beam. You're listening to SpaceTime. I'm Stuart Gary. Okay, let's take a break from the show while I tell you about one of our sponsors, the Great Courses Plus. Smart people love digging into interesting topics, learning as much as you can. But you don't always have the time or money to go back to school or university. And that's where the Great Courses Plus comes in. It lets you learn about stuff that interests you from the leading professors and experts in their fields. like this great course I've been doing, Redefining Reality, the Intellectual Implications of Modern Science. The course is taught by Dr. Stephen Gimbel, Professor of Philosophy at Gettysburg College. It sets about answering the question, is technology changing who we are? It looks at the discovery of dark matter, dark energy, the search for extraterrestrial life, as well as the historical aspects of philosophy and the arts. Just where are humans heading? This is a wonderful course to get started with from the Great Courses Plus. But there are over 10,000 lectures to choose from on so many different topics, not just astronomy and physics. There's engineering, history, the arts, how to play chess, how to draw, or what about taking better photos? Have you checked out the fundamentals of photography? You'll get taught how to take better pictures by a National Geographic photographer. There's nobody better. You'll learn great tips and tricks like how to use better lighting, how to really frame your photos no matter what type of camera you're using. Do you know what the thirds rule in photography is? Well, you can if you take the Great Courses Plus. In fact, you'll get unlimited access to stream their entire library. And of course, you can watch or listen anytime, anywhere with the Great Courses Plus app. And we have a special offer for our SpaceTime listeners. You can have an entire month of the Great Courses Plus for free. You can stream as many of the more than 10,000 lectures they have as often as you want. It's all free for a month of unlimited access. But to get this free month, you'll need to go to our special URL. So sign up now at thegreatcoursesplus.com/space. That's thegreatcoursesplus.com/space. And by signing up with the Great Courses Plus, you're helping to support our show. That's thegreatcoursesplus.com/space. And of course, we'll include the link in the show notes. And now, it's back to our show. Blue Origin has undertaken its first new Shepard flight for 2018, successfully pushing the envelope to an altitude of over 107 kilometres. That's 351,000 feet. The flight, which had been delayed by an hour due to thunderstorms, was the 8th from the company's Texas launch site. It brings Blue Origin a step closer to its goal of providing ballistic suborbital flights for space tourists. The internationally recognised official start of space is the Kármán line at an altitude of 100 kilometres or 330,000 feet. Above this point, aircraft can no longer be controlled by aerodynamic forces such as wings, spoilers, rudders, elevators and ailerons. Instead, they become spacecraft, needing thruster-powered manoeuvring systems instead.
It's time to hand it over to Mission Control and listen in on the final countdown. It is go time, New Shepard.
Guidance to internal. T-minus 10, 9, 8, 7, 6, 5, 4. Command engine start. 2, 1.
Listen to that engine rumble. Mission Control has confirmed New Shepard has cleared the tower on its way to space from the West Texas desert. All right, our first milestone, we're going to hit max Q. That's the point where aerodynamic stresses on the vehicle are at its maximum. Max Q confirmed. New Shepard as she gains speed towards our maximum apogee altitude of 350,000 feet today. 8th mission in this new Shepard test program. Launch is looking nominal from here. Clean burn on the BE-3 engine. Our next milestone is going to be main engine cutoff. We're going to cut off that BE-3 engine.
The new Shepard single hydrogen-fueled BE-3 engine was fired for 2 minutes and 16 seconds, blasting the spacecraft high into the air before main engine cutoff from MECO, followed 20 seconds later by stage separation.
All right, MECO confirmed, main engine cutoff confirmed. If you're an astronaut in our capsule, at this point, you're going to start to feel that weightlessness. Next up, we're going to separate the crew capsule from the booster. Separation is complete. There goes the booster. We've confirmed separation. So we're just waiting for apogee here. We're going to hit apogee because that's when, in fact, the speed goes to 0. And then, of course, it's going to start to speed up as the craft come back down to land. The two craft, the capsule on your right, the booster on the left.
As the capsule continued climbing towards the apex of its flight path, the new Shepard launch stage, known as the propulsion module, returned to the ground, undertaking a pinpoint landing 7 minutes after launch.
Now the capsule and the booster are racing back home. The capsule is going to land just a bit after the booster. The booster, of course, is more aerodynamically shaped. The booster shortly here is going to hit atmospheric pierce point. So that means that's when the control surfaces are actually going to have some air pressure to be able to work against to guide the rocket back to its landing pad. So I'm hearing from the control room that We might have actually hit our goal of 350,000 feet. A beautiful launch so far for the team. Those wedge fins on the forward section of the rocket have deployed. Those, again, are helping the rocket in its stabilization as it comes back into land. Shortly here, we're going to have the drag brakes deploy. Watch how it dramatically cuts the speed of the rocket as it comes into land. There go the drag brakes. Boom, we hear the sonic boom down here in Texas. Engine relight confirmed. And touchdown! Welcome home, New Shepard. Beautiful landing.
Meanwhile, the capsule, loaded with scientific equipment and testing apparatus, climbed some 20,000 feet higher than previous flights before beginning its own fall back to Earth and landing under 3 parachute canopies 10 minutes after launch.
Mannequin Skywalker up there getting some beautiful views. We're not going to let him out of his seat today, but you know he's getting to see the beautiful limb of the Earth out of those gorgeous windows. Again, second flight of that crew capsule with the windows. All eyes are on the capsule, so we're first waiting for the drogue chutes to come out. Those are kind of like the guiding parachutes. They are followed shortly by the mains, and after full inflation, the capsule will come in at a nice, steady 15 or 20 miles an hour for a smooth descent. There go the 3 drogues, and there go the mains. A nice, clean inflation. The speed comes down just at about 16 miles an hour. You can only imagine the view that Mannequin Skywalker has out of those windows as he slowly descends into the valley here in West Texas. In the last milliseconds, we're going to have the retrothrust system fire. It's going to kick up the dust, but really the capsule comes in at just about 1 or 2 miles an hour. So it's a nice, smooth landing. And touchdown. Beautiful soft landing for our crew capsule. What a beautiful mission down here in West Texas. Congratulations to the Blue Origin team. Another spectacular test mission. It looks nominal from here. There is the rocket back on its landing pad and the crew capsule sitting nice and pretty in the West Texas desert.
As well as carrying Blue Origin's test flight dummy Mannequin Skywalker on his second space flight, the capsule also included experiments for several companies and organizations, including NASA and the German space agency DLR. NASA's payload was designed to monitor cabin conditions during the flight, while DLR carried biology and physics experiments for several universities. DLR carried physics and biology experiments for several universities, and Solstar, one of the private companies, tested a new technology Wi-Fi system in space. I'm Stuart Gary. This is SpaceTime. China has launched the first part of the nation's most important lunar mission to date. It's an orbiter which will relay data from a lander destined to touch down on the far side of the moon later this year. The mission was launched on a Long March 4C rocket from the Xichang Satellite Launch Center in Sichuan Province in southwestern China. The orbiter, called Qi, Mandarin for Magpie Bridge, will provide a vital communications link between Beijing mission managers and the upcoming Chang'e 4 lander and robotic lunar rover, slated for launch towards the end of the year. Chang'e 4 takes its name from the lunar goddess of Chinese mythology. It's expected to land in the South Pole Aitken Basin, the largest known crater in the solar system, from where it will undertake a detailed mineral survey. A sample return mission, Chang'e 5, is slated for launch next year. China's ambitious lunar exploration program has already included the Chang'e 1 in 2007 and Chang'e 2 in 2010. Beijing's last moon mission in 2013 saw the Chang'e 3 deliver the U2 lunar rover to the moon's surface. U2, Mandarin for Jade Rabbit, was to land at Sinusaridum, but ended up descending into the Mare Imbrium 40 kilometres away instead. Although it encountered some serious difficulties on its second lunar day, U2 continued operating as a stationary science platform for a record 31 months, well beyond its expected 3-month lifespan. Beijing expect to have a permanent space station in Earth orbit by 2022, followed by a manned base on the Moon, and eventually lunar mining operations for helium-3. Because of its gravitational proximity to the Earth, the Moon is tidally locked with the same side always facing the Earth as the Moon undertakes its 27.8-day orbit around our planet. The far side of the Moon, sometimes figuratively known as the dark side of the Moon, is the lunar hemisphere that's always facing away from the Earth. The far side's terrain is very different from the near side, very rugged with a multitude of impact craters and relatively few flat lunar mare, which are so characteristic of the near side. Although both sides of the moon experience 2 weeks of daylight followed by 2 weeks of night, the far side is often wrongly referred to as the dark side of the moon. Although I guess technically dark could mean unknown or unseen, rather than lacking daylight. You're listening to Space Time. I'm Stuart Gary. And time now for June Skywatch. June, of course, is the 6th month of the year, the 4th month in the old Roman calendar, and it's named after Julius Caesar. It's a great time to look up the night skies and marvel at the majesty of the Milky Way as it puts on a spectacular overhead display. Of course, June also marks the winter solstice in the southern hemisphere, and of course it means the arrival of summer for our lucky listeners north of the equator, which this year happens at precisely 20:07 Australian Eastern Standard Time, Thursday, June the 21st. That's 10:07 AM Greenwich Mean Time and 6:07 in the morning US Eastern Daylight Time. The June solstice occurs when the sun reaches its most northerly point in the sky as seen from Earth, zenith appearing to be directly over the Tropic of Cancer. Of course, the seasons are governed by the tilt of Earth's axis as it journeys around the sun in a year. On the day of the June solstice, Earth's south pole is tilted by roughly 23.5 degrees away from the sun. That means the sun rises north of east and sets north of west. When the south pole's tilted towards the sun, it's the southern hemisphere's summer, and 6 months later, like now, when the south pole's tilted away from the sun, it's our winter. Between these two, we have the autumn and spring equinox. Temperatures on Earth aren't determined by Earth's orbital distance from the sun, but rather by the angle of the sun's rays striking the Earth. In summer, the sun is high in the sky and the rays hit the Earth at a really steep angle, while in winter, the sun's lower down in the sky and the rays strike the Earth at a far shallower angle. In most parts of the world, the seasons begin on the day of the solstice or equinox. Of course, Australia has to be different. Its seasons always start on the first calendar day of the month. March for autumn, June for winter, September for spring, and December for summer. Almost overhead this time of the year, we have the constellation Virgo. Virgo was the goddess of justice and the harvest in ancient Greek mythology, using her scales to weigh good and evil. However, she became disenchanted with the evil deeds of men, throwing away her scales and retreating to the heavens. Interestingly, the ancient Egyptians also associated Virgo with agriculture. To them, she was the goddess Isis, who spiked the heads of wheat across the sky, forming the Milky Way. To science, Virgo is a tightly packed region containing some 2,000 galaxies, all gravitationally bound into a giant galaxy cluster around 60 million light-years away. Our local group of galaxies, which includes Andromeda, the Milky Way, and about 80 others, is simply an outlying member of this cluster. This Virgo cluster we're part of is at the very heart of the Virgo Super Cluster, one of the largest known structures in the universe. The mass of the Virgo supercluster is so great that its gravity generates the Virgo-centric flow, causing our galaxy as well as Andromeda and all the other members of the local group to move towards the supercluster at about 400 kilometres per second. And that's despite the accelerated expansion of the universe moving everything further apart over cosmic timescales. It's now thought the Virgo supercluster, as big as it is, may simply be a lobe of an even bigger galaxy supercluster called Laniakea, the centre of which is known as the Great Attractor. Despite the Virgo cluster's size, it's so far away from us, it's really very hard to see without a decent backyard telescope. In fact, you'll need something at least 100 millimetres in diameter or larger. Also directly overhead, but a lot closer, is the constellation Corvus the Crow. Greek mythology tells us Corvus could talk to humans, but he was a lazy bird. And so Apollo took away his ability to speak and banished him to the heavens. As scientists study the crow, that's the bird, not the constellation, they've discovered that crows are incredibly intelligent, able to undertake quite complex problem-solving skills. Back to the heavens, and one of the highlights in the constellation Virgo and Corvus is the spectacular Sombrero Galaxy M104. Visible with a good pair of binoculars, this stunning spiral galaxy is seen almost edge-on, providing a spectacular backlit view of the galaxy's bold stars and the striking gas and dust lanes in its arms. M104 is located some 31 million light-years away, and is moving away from the Milky Way at about 1,000 kilometres per second. A light year is just shy of 10 trillion kilometres, the distance a photon can travel in a year at the speed of light, which is about 300,000 kilometres per second in a vacuum and the ultimate speed limit of the universe. The Sombrero Galaxy has a diameter of about 50,000 light years, making it about 30% the size of the Milky Way. It's surrounded by up to 2,000 globular clusters and an active central supermassive black hole at least 1 billion times the mass of our Sun. Now, by comparison, Sagittarius A star, the supermassive black hole at the centre of our own Milky Way galaxy, has just 4.3 million solar masses. Globular clusters are tight balls comprising millions of stars, all of which were originally formed at the same time in the same collapsing molecular gas and dust cloud. Globular clusters are usually also quite old. Being so gravitationally bound, the stars in the cluster have never had a chance to spread apart. The brightest star in the constellation Virgo is Spica. It's a spectroscopic binary, located about 250 light-years away. Spectroscopic binaries are pairs of stars orbiting too close to each other to be separated by telescopes, and instead are distinguished by the Doppler shift they display in their spectral signatures, showing that there are two stars present. The two stars in Spica are so close together they're orbiting each other every 4 Earth days, and their gravitational interaction has caused them to become rotating ellipsoidal variables, in other words, egg-shaped. The primary star is a variable blue-white giant about 10 times the mass of our Sun, and about 7.5 times its diameter. Once a spectral type B main sequence star, it's now some 12,100 times the Sun's luminosity. The giant star is now pulsating rapidly and rotating at over 199 kilometres per second over a 0.1738 Earth day period. In fact, it's one of the nearest stars to Earth, expected to end its life as a core collapse or Type II supernova. The second star in Spica is also thought to be a spectral type B blue-white giant, with about 7 times the mass and 3.6 times the Sun's diameter. Looking about 20 degrees above the western horizon in the early evening is the fourth brightest celestial object in the sky, the dog star Sirius. To the northwest or right of Sirius is another fairly bright star called Procyon, the brightest star in the constellation Canis Minor, the lesser dog. In Greek mythology, Canis Major and Canis Minor were Orion's hunting dogs. Located some 11.6 light-years away, Procyon is another double-star system, comprising a spectral type F white-yellow star, Procyon A, and a faint white dwarf star, Procyon B. Procyon A is about 50% more massive than the Sun, and has about twice the Sun's radius. However, it's unusually bright for its mass. That suggests it's evolving into a subgiant that's fused nearly all of its core hydrogen into helium. And what that means is that it will soon expand into a red giant. Mind you, in astronomical terms, soon means sometime in the next 100 million years. When it does so, it'll increase its diameter by up to 150 times its current size. The white dwarf, Procyon B, has about half the Sun's mass and a diameter of about 8,600 kilometres. The pair orbit each other every 41 Earth years at an average distance of 15 astronomical units, about the distance of Uranus's orbit around the Sun. About 25 degrees above the north-northeastern horizon this time of year, you'll find the bright star Arcturus, the brightest star in the constellation Bootes, the ploughman or herdsman, and the fourth brightest star in the night sky. Located just 36.7 light-years away, Arcturus is a bloated, aging red giant, about 7.1 billion years old. Having used up all its core hydrogen, it's now fusing helium into carbon and oxygen. Now, this has caused the star, which is only slightly more massive than the Sun, to expand out to about 25 times the Sun's diameter and become about 170 times as luminous. In Greek mythology, Arcturus was the guardian of the bear. This is a reference to it being next to the constellations Ursa Major and Ursa Minor, the greater and lesser bears. There are some indications Arcturus could have a binary stellar companion, but the results at this stage are still too inconclusive. There's also speculation it could have a large planet or small substellar object about 12 Jupiter masses orbiting it. That makes it pretty close in size to a brown dwarf, but yet again the research remains inconclusive. Turning to the east now, and the 3 bright stars in the constellation Libra, the Scales of Justice, are visible about halfway or 40 degrees above the horizon. These represent the claws of Scorpius the Scorpion, which is chasing Orion across the sky. If you look directly south now, you'll see the star Polaris Australis, or more accurately Sigma Octantis, the nearest star to the southern celestial pole, and consequently the counterpart of the North Pole star Polaris. However, Sigma Octantis is far harder to see than Polaris because it's much fainter. Located some 270 light-years away, It's an orange giant nearing the end of its life. Joining us now is Jonathan Nally, editor of Australian Sky and Telescope magazine, for the rest of our tour through the June night skies.
G'day, Stuart. Yeah, well, in June, the evening begins with the Milky Way, our galaxy, stretching across the sky from east to west. That's, after the sun's gone down, give it a couple of hours or so, nice and dark, and all people have turned out some lights. You'll see the Milky Way going all across the sky from the east to the west. The Southern Cross, for once, is standing upright in the sky at that time of night. It's about 2/3 of the way up from the southern horizon. As the night goes on, it'll tilt over a bit to its right or to the west and go a little bit more onto its side. But right at the moment, mid-evening, it's nice and high and standing upright. Over in the west, above the horizon, is the brightest star in the night sky. That's Sirius. And a little bit around to the southwest of that is another brighter star, the second brightest star in the night sky, actually called Canopus in the constellation Carina. If you have really dark skies and you've got a clear southern horizon, look south and see if you can spot the two Magellanic Cloud galaxies down low. They're very faint, and they just look like sort of dull smudges or clouds. Sometimes it's even good if you don't look directly at them, just sort of look a little bit to the side, look out the corner of your eye. You'll be able to spot them, and these are actually the nearest sizable galaxies to our own. They're called the Magellanic Clouds after the explorer Magellan. Up in the northern half of the sky, it all seems quite bare at this time of year, at least in the sort of mid-evening hours through to about midnight or so. The bright star Arcturus can be seen about halfway up from the northern horizon, almost directly overhead in sort of mid-evening at the beginning of June. You can see another bright star, that's Spica. As the night goes on, though, you'll see that things have changed. By midnight, Sirius has set in the west, it's gone down as the Earth has turned. The bright stars Vega and Altair will have appeared in the north, and there's another star right down the southeast called Achernar. That's popped up above the horizon. And the Milky Way now, from midnight onwards, is now stretching from north to south. So there's nothing actually happening out there in space. It's just that the Earth is turning, right, on its axis, and the things that were below the horizon a few hours ago have now come into view, and some of the things that were in view down on the western horizon, they've now gone down below the horizon as the Earth is turning. Now, this month, June 2018, is a pretty good time to see the planets, actually. At evening twilight, have a look out to the west. You'll see Venus. You cannot miss it. It's the biggest and brightest thing that you'll see in the sky, other than the moon. It's when it's around. It'll be there all month too, Venus. So if you're looking for Venus, you want to spot Venus and it's cloudy or whatever, well, don't worry. It's going to be there all month above the western horizon after the sun has gone down. Mercury's out there too, and just above the western horizon all month, or most of the month, down very low, but quite hard to see because it is very low and it's sort of lost in the glare of the evening twilight a bit. But the three other planets, Jupiter, Saturn and Mars, are all visible in the evening sky this month. At the start of June, Jupiter is high overhead and shining really brightly. Saturn is about halfway down towards the eastern horizon, and halfway again is the planet Mars. Now, we've spoken before on the show, haven't we, about opposition? Mm-hmm. Opposition is when the sun and a planet are in opposite directions in the sky as seen from the Earth. Saturn reaches opposition this month on the 27th. So on that day, as the sun is sinking in the west, Saturn will rise in the east. You'll have all night to observe it. But you don't have to just go and look on that night, the 27th. Weeks either side doesn't matter because Saturn's not changing its position in the sky very much. So, any time leading up to then, in the few weeks beforehand and the few weeks after, even a couple of months after, doesn't really matter. You can have a really good view of Saturn. Jupiter was at opposition last month in May, and Mars is going to be at opposition next month, July. And it's going to be a really good opposition too. In fact, it'll be the best view we've had of Mars since 2003.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And this is SpaceTime. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with a science report. New data shows that 9 out of 10 people worldwide are now breathing air containing high levels of pollutants, and some 7 million people are dying every year because of air pollution. The findings are based on new data collected by the World Health Organization. Scientists say the research shows that air pollution is causing an estimated 24% of all adult deaths from heart disease, 25% from stroke, 43% from chronic obstructive pulmonary disease, and 29% from lung cancer. The Australian Bureau of Meteorology warns that its ability to accurately measure and forecast weather will be affected by federal government plans to force changes to the 5.6 GHz band currently used for weather radar measurements. Trials of the new 5G cell phone on the Gold Coast near Brisbane and in Parramatta in Western Sydney are seeing data speeds between 3.5 and 4 times faster than the existing 4G network. The government plans to auction off parts of the 3.6 GHz band in October for the new 5G network. However, in order to do this, Canberra will need to move some existing internet service providers now on the 3.6 GHz band to a new home. The Australian Communications and Media Authority, ACMA, has proposed moving them to space in the 5.6 GHz band, now being used by the Bureau of Meteorology's weather radar. The point is, the 5.6 GHz band is especially good for radar reflectivity, for detecting interactions with water droplets in the atmosphere. So, moving ISPs into this band will affect the weather radar system's range, resolution and measurement accuracy. It means radio signal leakage from the adjacent ISP spectrum will hinder weather radar's ability to detect distant rain particles, meaning it could start detecting storms that aren't really there. Scientists have finally solved the long-standing mystery of why the Leaning Tower of Pisa continues to somehow survive the numerous strong earthquakes which have hit the region over the centuries. Apparently, it's just not shaken with a rhythm. Despite leaning precariously at a 5-degree angle, leading to an offset at the top of over 5 metres, the 58-metre tall tower has managed to survive undamaged at least 4 strong earthquakes which have hit the region since 1280. Given the vulnerability of the structure, which barely manages to stand vertically and needs considerable structural reinforcement not to fall over, it was expected to sustain significant damage or even collapse due to seismic activity. Now, engineers and other scientists attending the European Conference of Earthquake Engineering have been told the bell tower's survival can be attributed to a phenomenon known as dynamic soil-structure interaction. It seems the height and stiffness of the tower, combined with the softness of the foundation soil, causes vibrational characteristics in the structure to be modified substantially, in such a way that the tower simply doesn't resonate with the earthquake ground motion. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.